All right. Recording. Python. Yes! My favorite. There's got to be a way to hide this. Anyone here use Zoom? Yeah, whatever. All right. Python. The third. If you're not on sensors, just watch. Maybe you learn something. Maybe you have a very special interest in Python. Come talk to me about it. You want to do the homework anyway? I'll still give you a grade. That's fine. What are we going to talk about today? Your previous homework. I didn't count how many of you landed the rocket. It wasn't all of you. Some of you submitted your homework 15 minutes ago. These are the people who land the rocket with one fuel left. Always wait till the last minute. We're going to talk about constants. What is a constant? Why do we care? Talk about variables. They're not constants. What is dependency? Why do we care? Multiple return functions. It's like a regular function, but better. Minimum and maximum. These are just some tips and tricks common in Python. Some of you already know about these. I saw it in your homework. You know who you are. We're going to talk about dictionaries. These are so cool. It's similar to a struct, if you know C, like I do. All right, rocket lander homework. First, maximum credit to JJ. Nerd. But no, this is useful skill. If you fail as a programmer, you can get a job in the Air Force flying the rockets. We're going to talk about code duplication. There was a lot of that in the homework. We're going to talk about extra variables and things that were never used. A lot of that in the homework. We're going to talk about flow control. And we're going to talk about the future of homework, which, as I said, only some of you have to do. The others, you can still do it if you want. But first, what is this? This is my mantra. You are the sum of your projects. Everyone knows what a sum is? You add two things together, you get the sum. 2 plus 2 is 4. 4 is the sum. You are the sum of your projects. After college, you go, yes, Neil, write this down. After college, you go to your first job interview. They say, oh, your grades look very good. What projects have you done? You say, I haven't done anything. They send you away. You're useless. Maybe not useless, but what good are you? I don't know. But instead, you say, oh, I did this very cool rocket lander game. They say, oh, I would like to play your game. This game will demonstrate your abilities more than getting an A in the class, because maybe you give your professor $50. You get the A. It doesn't show up on your transcript. You show up with a cool game. Everyone knows you're awesome. The same thing will be true of your IoT project at the end of the summer. They say, oh, well, your game is cool, but have you ever done any work with analog sensors? And you say, oh, yes, lots. When I was in America over the summer, I worked on an air quality sensor. And, and they say, oh, that's so cool. We need someone with your skills. That's why we're here, to do more projects. These are the two things that matter. What you can do, this is the most important if someone doesn't know you. The first time you meet someone, the only value is what can you do? The best way to show them is what have you done? The second most important thing is what can you learn, and also how quickly. If you say, oh, I'm really good at VHDL, it doesn't matter if you don't know what this is. I'm really good at VHDL. I can't do anything else. They say, that's okay, it's good, it's not great. We need someone who can do VHDL today. Maybe tomorrow we need someone who can do Verilog. So we'll fire you on Tuesday and hire someone else who can do both. But if you say, oh, I don't know Verilog, but I can learn it tonight. They won't fire you. This happened to me. I was at a company. They said, hey, we need someone who can use this new programming language. Do you know this language? And I said, no. And they said, can you learn it? And I said, yes. And that was my job for a whole month. Turns out, nobody knows that language. It's new. But if you learn it quickly, very valuable. Okay, back to what really matters. Rocket landing. Constants. This is a constant. It's called gravity. It never changes. You'll notice something is different about this one. It's all in capitals. This is a clue because Python doesn't really have constants. In C or C++, you can have a constant. You just call it a constant. You say, this is gravity. It's a constant. If you try to change that value later in your code, it will yell at you and say, hey, that's a constant. You told me never to let you change it. Now you're trying to change it. It's stopping you. In Python, there's nothing to stop you. You can say gravity is -10 or -9.81 meters per second squared. And then later you change your mind. You say, no, it's back to 10. Python is okay with that. I'm not okay with that. You should have more discipline than this. This is why discipline matters. Remember I said what makes a good programmer? Discipline. Later in your code, you might find yourself changing gravity. Gravity equals -10. And you say, why is the computer shouting at me? That's how we do it in English. I don't know what the equivalent is in Korea, but you're really angry at someone. You send them an email. You type the whole thing in capitals. You say, hey, screw you. In all capitals, they know you're serious. You're shouting at them. The same thing here. You're trying to change a constant. Why is it shouting at you? Because you shouldn't do that. That's really all we're going to talk about, constants. It will totally work if you don't capitalize it, but you should do it. This is a common convention. You're reading someone else's code. You see they got a lot of capital letters in it. This is why. Okay, the rocket lander. This is how I did it. Some of you did it almost the exact same way. I'm proud of you. Some of you did it a better way. I'm proud of you. Some of you did it in like 300 lines. I'm proud of you. Here's how I did it. 50 lines. That also includes my name at the top. So maybe it's fewer lines than that. Not that number of lines is the best metric, but I like to think it's good. What have I done? I printed the position of everything. The position, the fuel, the velocity, all of it. Then I checked the position. This is my while loop. This is the only while loop. We check the position to see if the rocket has landed. If it hasn't landed, well, you better land it. If we've got fuel, get the thrust. If there's no fuel, skip to the next step. And then we update our state. We got some equations here. I sent these to you in the email. Then we print the state again. The astute viewer will say, hey, you printed the state up here and also down here. You could use a function for that. You are correct. And then the last thing I do is print the result. Did you land it? Did you blow it? Some of you blew it on your homework. The rocket, it landed right on the Capitol. Very sad. Everyone's dead. Okay. Let's get into the details. These are some variables. What is dependency? Why does it matter? When I sent you the first email with the assignment, I had some explicit equations in there that says the new fuel is equal to the old fuel minus the thrust, as it is done here. The old fuel is the fuel, and then the new fuel is the old fuel minus the thrust. However, some of you quickly realized you don't need to hold on to both of these because nothing else uses the fuel for the calculations. You could do it with one line and just subtract the thrust from the existing fuel and put it right back in the same spot. The same with the position. Turns out nothing depends on the position. You don't need to store both of them. Is it really better to have fewer variables? In this case, it doesn't really make a difference, but later you're going to work with some giant arrays, 500, 10,000, 1 million elements. You don't want to duplicate it if you don't have to. This is a good spot to learn what's necessary, what's not necessary. Next. Oh, one more. The speed, sometimes called the velocity. You might say, but the velocity was very important in something else. We used it to calculate the position. That's true. However, we don't update it until afterwards, so you don't need to keep the new and the old simultaneously. So here, these are the equations that I gave you guys. Here is a super compact version. You take the old fuel, you subtract the thrusters, you put it back in the same spot. Awesome. Acceleration. You do the same thing. Well, acceleration, actually, you don't need to hold on to the old acceleration. That's cool. Maybe we'll include that in a future version of the assignment. Position, here's the same formula. Self-explanatory. Okay, let's talk about reusing code. Another great use of functions. I'm not going to say who, but one of you submitted this in your homework, and you can't see the lines here, but at lines 44, 54, and 58, you show the rocket status. That's excellent that you wrote it as a function, and so you only have to write out the whole thing once and then print it several times. Maybe you can rewrite the code so you don't need to print it so many times. That's okay. This is excellent. Then if you decide, oh, I don't want to do this with meters, I want to do it in feet. I don't want to use double quotes. I want to use single quotes. I want to change the order. You only have to change it in one spot. Excellent use. Some of you, not going to say who, I saw in your code you type out the same thing 10 times. And then, maybe not 10 times, maybe 4 times, I think was the most that I saw. And then you decide, oh, I want to change it in one place. I have to change it in all of the places. Ugh. Takes forever. Okay. Here's another great use of functions. You can simplify your code. You might say, does this really save a lot of space? No, it doesn't, but it sure does make your code easier to read. Someone else picks up your game and says, I don't know anything about rockets. How the hell does this work? And they can see here, oh, first you get the thrust, then you get the new acceleration. You calculate it with this intuitively named function, calculate acceleration. And then you calculate the velocity with this intuitively named function, calculate velocity. And if the person reading your code is an enormous nerd and loves physics, as I do, then they can go back into the definitions and see what your calculations really involve. Oh, so cool. They'll be disappointed that it's so simple. But anyway, you'll notice here that gravity and thrust both come from outside of the function. You might say, but Mark, the scope. We'll talk about it, but not right now. Another great use of functions. Here's how you calculate the position. You might say, this is not the formula that you gave to us on Thursday, Friday, I don't remember, Wednesday? That is correct. This is a new, much more exciting and much more complete formula for the position. which you will use in your next homework assignment. Yes! But this is a nice thing. If you had the old position formula, and then I say, hey, I'm an asshole, we make the physics more complicated. Here's the new formula. It's right there. All you have to do is change it. If you've got it at 10 points in your code, you just change it in the one spot. Done. Awesome. Next. All right, here's a good example of code reuse. Not going to say whose homework this is, but you might look at it and say, hey, that looks like my homework. Look at these two red boxes here. They look the same. The reason for this, they are the same. This is a prime example. If, like an asshole, I change the functions, you would have to change it twice. Or, like a noob, you got the functions incorrect. You would have to change it twice. But not if you put it in one function and call them all at the same time. Next. Wait, everyone see why I'm angry about this? I'm not angry, but why this is important. Here's how we would do that with a function. All right, this is why I wanted you guys and girls on sensors to sit in the front, because some of this is, I need the whole screen now. So this is how it was done before. We declare all our states here. Our variables here. We got our gravity as a constant. I'm just going to calculate the new variables. This is taken straight out of my code. Well, I just update the fuel. Boy, there's a lot of lag on this. I update the fuel, update the acceleration, calculate the new position. If the position is actually negative, we bring that up to 0. Some of you noticed that in my code. I should say in the sample games that I distributed with the assignment, that if the position is negative because you've crashed or landed, then I stopped it at 0. And you did the same thing. Well done. Some of you didn't notice. I tried to help you where I could. I didn't answer all the emails. Very sorry if I missed you. And here's how you would do that with a function. I've just taken all of this crap and put it in a new function called calculate new state variables. And we've updated the fuel the same way and the acceleration. And then when I call it, I just gotta call this one line. However, you will see we got all kind of nasty errors here. What the hell is going on? It's the same code. Now it's in a function. What have we done wrong to displease the Python gods? I'm glad you asked. This first one here is not really an error. It's just a warning. Your code will run fine if you don't fix it. But PyCharm will tell you, you only have one blank line. You should have 2 blank lines. And in other places, it will tell you, you only have 1 space. You should have 2 spaces, or more often, you have 0 and you should have 1. You can ignore these, but please don't. Just fix them. They're free. Okay, what's the next warning or error or whatever? Shadow's name. Everyone knows what a shadow is? Everyone? Anyone doesn't know what a shadow is in English? I don't know the Korean word for shadow. Song, loudly for the class. Shadow in Korean. Louder. Thank you. That's a shadow. PyCharm's going to give you an arrow and say, hey, you shadowed a name that was declared outside the function. What does this mean? It means you use the same variable name, not actually the same variable. So in this function, the scope of this function, first we define the name, we give it a colon, and at this moment the function knows nothing except what is already declared out here. And if you declare something else with the same name, it has no way of knowing which one you're talking about, and it will give a preference to the one that you just made. So here, thrust, it recalls from outside, which is fine. But here, acceleration, it says, hey, I know you had an acceleration, but you're also trying to change the value of acceleration, which normally you don't do inside of a function unless you're using pointers. We won't talk about it. The expectation is if you want to get a useful number from a function, you return it. You don't just assign it directly. So here, Python believes that you are making a new variable, which only this function can see, and you're calling it, by coincidence, the same name. If you later try to compare them, Python could get confused. Next error. This is actually an error. It's called an unresolved reference. What is this? This is our red underline here. That's a real error. That will stop your code. An unresolved reference is where you're trying to use something in your code and it doesn't know what the hell you're talking about. Right here on the left, we get another shadow warning. It believes that you are creating a new variable with the exact same name as this one, and that's okay. It's just going to ignore this one. However, immediately afterward, you try to give it a value based on itself, and it says, this has no value. I just created it. How do we fix all of these errors? I want the code to be so sexy and use these functions. Here they are. The first thing I've done is use different names. You can see these are just abbreviations. If any of you were on the radio in Korea when you were in the army and you were using real sophisticated codes, you would notice that this is not a clever code. F, this is for fuel. T, this is for thrust. There's no confusion now. The program knows exactly what to do. However, it doesn't know what the initial values are. You've got to pass them in, which has other benefits, which we'll talk about. If you didn't want to pass them in, you could start by making duplicates and just say, hey, F equals fuel. And it will say, oh, I know fuel from outside. We're going to skip all of that. It's all done right here. Gravity, we can keep because we're not trying to assign a new value to it. Everything else is pretty much the same. This shouldn't be too complicated. But here we have 3 return values. What the hell? I didn't know you could do that with a function. Turns out you can. So we've got 4 inputs, 3 outputs. Nice. Minimum and maximum. These are built into Python. You can use them right away. I got 2 samples of code here. They do the same exact thing. This one we've calculated a value and then we check to see if it's less than 0. If it is, we fix it. Here I've done the same thing, but before I even stored the value, I compared it with 0 using this max function. What it does, you got 2 inputs separated by a comma. It takes the biggest one. Cool. But be careful. One of you, I'm not going to say who, but you were the first person to submit your homework. Nerd, also rocket expert, Mason. Wow, this is like impossible to read. I had to read it backwards from this side. Maybe you're smarter than I am. This very possible. You seem like a pretty smart guy. But please don't do this on your homework in the future, and no one else should either, because it's really difficult to read. Maybe if your text editor only shows 10 lines at once and you want to get the whole thing on one screen, you can do this. Don't submit this in your homework. Next. Ultra reuse. What the hell is that? That's something I just made up. Let's watch a video. Probably you've seen this before. I do not own the copyright to this video. I'm saying it because we're recording. All right, we got, holy crap, there's 2 rockets coming down. What? Come on. Rocket 1 lands first. Rocket 2 lands second. I was really generous with you guys. I let you land at 3 meters per second. These rockets, 3 meters per second, it's trash. You've got maybe 1 meter per second. But look, there's a 3rd rocket. Did you guys know that? 3 rockets. Can you imagine? Here the video cuts out, probably because the rocket is landing. Of course, I still love you. I don't want to spoil the suspense, so I'll just wait. And you could, ah! The 2nd rocket landed. Sorry, 3rd rocket. Very cool. And you might say, Mark, how many rockets do you want me to land in my next homework? All of them. All of the rockets should be land. Oh, Jesus, where's my slideshow at? Oh, thank God. We almost had a disaster. All right, back to where we were. Where the party never stops. Whoop. Okay, here I've created for 2 rockets. This is a list. You might recall this from our very first Python lecture. You've got 2 items. They're indexed 0 and 1. I'll do that with the mouse in case you're watching this later. 0 and 1. You want to call out the first one? This is how you do it. You want to call out the second one? This is how you do it. And now you're playing with 2 rockets at the same time. Same function, different arguments, different returns. So cool. If we had 50 rockets, can you imagine? If we had 50 rockets, that would be an excellent place to use a for loop, which I didn't force you to use in this homework. Maybe I will. Hint, hint. All right, dictionaries. What is a dictionary? Do you know this word in English? Probably. This is like the first language you learn, the first word you learn when you're learning another language. A dictionary. You got a lot of words, you got a lot of definitions. Python, no different. It's kind of like a list. Remember lists? It's kind of like a list. The main difference is that you don't have to call things by their number. How cool is that? So here, I'm making a dictionary. I'm calling it the state. Should I switch to the front camera and get a recording of this for the lecture? Nia, do you need some coffee? What time is it? 2:41. Everyone, break for coffee. Good thing I did that review. Acceleration is first. What the hell? So it turns out with a list, there is no order really. Sorry, not list. With a dictionary, list definitely has order. This is the whole purpose of a list. But with a dictionary, there's no order. You say, tell me everything, and it tells you in its own order. How is this order determined? The computer figures it out. I don't know, but it can change at any time. If you add another item to the list, you think it goes on the end, you're wrong. Maybe. But then if you call out specifically one element, you say, hey, I want the state, but just the position. It says, hey, I know this word. You told me. When you ask for position, I give you 100. There it is. I say, thank you. The astute observer noticed we got double quotes here, air quotes. But also here is the single quotes. In some languages, these are very different things. Not in Python. In Python, they're the same. Here I'm using double quotes to define my state dictionary, and I'm calling it by different quotes. Oh, you know this guy? That's okay. Who are you? Oh. Oh, very cool. I always wondered what was in there. I never looked. We should be charging him rent. What floor are you on? Fourth, okay. One floor, $100? Who's your PI? Professor John. Oh, okay. He has special privilege. We let him keep his stuff there. I don't want to cause trouble. Okay. So you see here, I define a position and velocity. I'm calling for the position with double quotes. I cut it off there, but it's 100. I'm calling for position with single quotes, the same thing. But here, I've called for what? A single quote and then a double. I don't even just. Oh my goodness. 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 Oh my, don't do that. Oh my goodness. I am ashamed. What happens if you do this? Two things will happen. The first thing is PyCharm will yell at you. It'll say, hey, what the hell are you doing? The second thing it will do is it will get stuck. And it will just stay there until you forcefully quit it, either with Control-C or with the big red stop button. That's my favorite button. All right, more about dictionaries. You don't have to write it all out in one go. You can see in the first time I did this, it was really long. Here, it's been made somewhat shorter by using shorter names, but you can make it really short and easy to read by having a nice column like this. I like to do it this way because it makes it easier to read. You can do it because of these curly braces. Everyone see that? It's got the little point on the end there. It's not a bracket, not a parenthesis. Curly brace, you can split lines. Because remember, Python always respects the white space. This is basically saying, shut up about your white space. I'm going to use multiple lines, deal with it. I'll tell you when to stop. Okay. What can you do with a dictionary now that you've got one? Well, the first thing you can do is you can check and see what's in it. So here, you can see I've already made a dictionary called state. Previous page, you can check it out on your own. And it's got a position, it's got a velocity. And if I didn't know this, but I was curious, I don't want to look like a fool asking for the position before I know it has a position. Then you say position in state, and it will say that's true, there is. And then you get greedy. You say acceleration too, and it says no. Don't ask for the acceleration. I don't know what that is, but later I will teach you how to put one in. This is a very cool function. This is so cool. Here's how you add things. Let's say you've already got your state, you've got a position, you've got a velocity. Is it a rock? Is it a rocket? Is it rock and roll? I don't know. I want to be sure. I'm going to just give it a name, which I call here name. When you do this, it says, hey, I see you're trying to give this thing a name. It doesn't have one. I'm going to give it one. If it already had one, you would just replace it. It does not matter. And now, if I say, tell me everything you know, it says, this is my position, this is my name, this is my velocity. Notice that the name didn't go on the end. Weird. Doesn't really matter for how we're going to use it. You can see how excited I am about this. This is serious business. If you define a state like this in C, using a struct or a union or whatever, and you try to add an element, you can't do it. C hates you. If you're rewatching this video, I just paused to drink from my thermos. All right, the last example about dictionaries. We have one very nice, very large function here. What does it do? It's going to update the state. And it takes as an input a state. But it doesn't know, like, even though I'm expecting a state, you could pass it something illegal. You could make an error in your code and not discover it for some time until you really need to update the state. So the first thing we'll do is check to make sure that this is a valid state, that it has a position, and that it has a velocity, and that it has an acceleration, and that it has fuel, and that it has thrust. Did you guys know in English there used to be one more letter and it made a sound? They called it thorn because it sounds like the first sound in the word thorn. It's gone. We just use the T and the H now. And so here I'm doing my update just as before. The fuel is equal to the old fuel minus the thrust. Acceleration is equal to gravity plus the thrust, position, etc., and so forth. This all look very familiar to you. If you figured these out when you were doing the homework, good job, I'm proud of you. If you didn't, now you know. You'll have another chance. And then I'm going to return S. In this case, I'm just returning the whole state. It gave me a state to start with. I made some changes to it. And then I give it back. Cool. But this was only if the state was good and it had everything that I needed. The first thing we do is we check. Can I do all these calculations? If we can't, spit it out. We're going to get this lovely message. We got an invalid input. You better fix that. And then I'm going to write out what it is in case you forgot, We gotta say something useful. And then I'm gonna return the S, the state. It comes back exactly as it was before. Let's talk about the next homework. Woo! Only 6 of you have to do the homework. This means if you come to office hours, I'll have plenty of time to help you because 20 people won't be there asking about the homework. For the other 20 of you, if you want to come to office hours just to practice your English, that's fine too. The first year I taught this course, there was no homework at all, and my office hours were packed because I know all the best English jokes, things you'll never hear on the radio, never see written on the internet. All right, you're gonna modify the rocket lander game. You can start with the one that you already built and just make some changes and put it up on GitHub. Just update it, track your changes, and in the comments section, you can say, I'm making this update because Mark is an asshole. He told me I need to expand the game. Whatever. Be grateful I'm not giving you a whole new assignment. You're gonna get the thrust from the users. You're gonna trim it as before, but now I want it in a single function. And then it's just gonna return the proper thrust level. You're gonna update all the state variables with brand new physics. If any of you have taken a physics course, I assume that you have. In America, everyone who goes to college takes this physics course their very first year to come up with these formulas. We can talk about these in depth if you want. There's some of my favorite stuff. The biggest change is we're going to add a time step, which for now you can define just as a constant. Start with 0.5 seconds. Otherwise, it'll just take too long to play your game. Unless we change the input method. Ooh, tomorrow's class will be very exciting if you're interested in that. And you can just see it's mostly the same formulas with a couple of changes. If t is 1 second, then it's exactly the same thing that you already did. And then you're going to print the rocket status. But now we have 2 rockets. The second rocket, it starts higher, but with a little more fuel. Question, do you believe that you could land a rocket with this much fuel? Physics says, oh, I'm not going to spoil it for you. We know that you can land a rocket from 100 meters using only 67 fuel. Could you just double the fuel and use 134 liters? Who knows these things? Special prize for the high score. Sorry, JJ, I don't have anything for you today. Figure something out. That's it. That's the whole lecture. Jeez. Well, we're way ahead of schedule. That's good, because we're going to talk about my second favorite thing. Who wants to guess what my second favorite thing is? Where my first favorite thing is sausage. Oh shit, I forgot snorkeling. Who wants to guess my third favorite thing after sausage and snorkeling? Anyone? Electronics. Yes! We're going to talk about the ADC. What is an ADC? Anybody knows? Sir, you are a nerd. Excellent. Welcome. We're glad to have you here. The analog to digital converter. These are excellent. because everything that you do in Python is digital. All of it. Everything is numbers. If you want to do something analog with Python, what you can do is convert it into digital and then do anything else. But the first step is always turning it into a number, digital. So, anyone here worked with ADCs before? Maybe another project? Anyone? Maybe? You must know something about ADCs. Yeah. What'd you do with the ADC? What? Electronics. What year are you? 4th year? 3rd year? Senior. Excellent. You know all about ADCs. You can go have a longer coffee break. Everyone else, yeah. You're welcome. I have 26 cents and this ring that I found on the ground. Okay, we're going to talk about, for everyone else, ADCs, analog to digital, converter, analog to digital. Wow, that's terrible. Converter, ADC. Whoop. Cool. How does an ADC work? These are so cool. We got our ADC right here. You got an analog voltage comes in here. You got a digital number comes out here. This is the analog side. This is going to be the digital side. I'm going to show you a really simple 2 bits ADC. No, we'll start with the most simple, the 1 bit ADC. Get rid of all this crap. I got some supplies on my ADC here. I'm going to say this one gets 1 volt. And of course, ground. I got my analog signal here. Who knows what it is? We got a little kind of a truth table here. This is going to be our input. This is going to be our output. If the input is between 0 and this number, the output is 0. If the input is between 0.5 and 1, the output is 1. How cool is that? Fact, this is how a digital read works. If you use digital read on Arduino, it's just a 1 bit ADC. Not very useful for any real analog stuff. Let's get more clever. 2 outputs. Nice. Get rid of all this. Now, I'm going to slice my possible inputs into 4 regions from 0 to 0 to 0.249, and then 0.25 to 0.499, and so forth. You can probably see where this is going. 0.75 to 1. And our output is just going to be a nice simple count. So cool. If you read this number in Python, this is the number 1. God, this is the number 0. This is the number 1. This is the number 2. This is the number 3. this is what you can do with 2 bits. So, why do we care? That's still not a lot of bits. Well, let me tell you. On the UDO Neo, we got 12. Cool. All right, so here's our analog input. Oh my God. Oh, first as I'm doing this, apologize to everyone. These were backwards. Whoops. I don't know how to count in binary. I'm just faking it. Here's our analog input. So we're going to start out here, Y11, Y10, and so forth, Y1 and Y0. And if your input is really small, probably less than a millivolt, 0.1 millivolts, you're going to get all outs. That's all 0 all the way across. I'm going to give ourselves a reference here, 3.3. This is what it is on the UDO, I believe. Around here, and we come up down here to 3.3 volts from 3.299, something like that. And we're going to get all ones on the output. In hexadecimal, this will look like, pardon me, well, not hexadecimal, in irregular digits. This is going to be 0. This is going to be 4,095. This is my favorite number. It's not my favorite number, but it is a really good number. So what we've done is we've sliced the input range from 3.3 to 0. We're going to map that to this. 4,095 down to 0. So when you measure something from an ADC, 2 things you need to know. The first, what is the actual digital number? You say, oh, I was reading this ADC and I came out with this number. It was 2,048. That's very cool. How many volts is that? I don't know. How do you know these things? You got to also know the scale. This is the most important number. You say, hey, my scale is 3.3 volts. I know that 3.3 volts is the same as 4,096. I'm not going to tell you why this 4,095 and 4,096 are not the same. If you're clever, you can figure it out. Hint. And what you get is, oh, that was 1.65 volts. Cool. Now I have something useful to do with that much, with that, that voltage. This is going to be really important for all you sensor nerds out there, because you're going to have to take so many analog measurements and then do some math with it. Yes! Okay. But also, in the UDO board, I lied a little bit. You don't have just the one analog input. You've actually got, I think, 6. Whoa, cool. What happens to these 6 inputs? I'm glad you asked. We're going to talk about my 4th favorite thing, multiplexers. Awesome. What is a multiplexer? It's like a switch. If you had a 1-bit multiplexer, it would look like this. We got 2 inputs, 1 output. I'm going to call this in 0, and this is going to be in 1, and this is just going to be the output. One thing is missing here. We got to have a select. S. That looks too much like a 5. I apologize. S for select. This is a digital input. When S is high, which is a logic 1, then the output is going to get straight from the input, like this. If select is low, then the output is going to get from this one, like this. Here, let me make a nice table for you here. This is S. Here's our output. When S is 0, the output is the same as in 0. When S is 1, the output is the same as in 1. Cool. This is special mux. It's an analog mux. There's two kinds of mux, analog and digital. The digital mux, it only passes digital values. It's not actually connecting the two outputs. It's reading one of them and making the output the same thing. Why does this matter? Well, here's a model for our analog mux. Oh, shame on me. We got an input 1. We got an input 2. We got a switch. We got another switch. And then they come to one output here. This is our mux. And then these two here, this one is going, this is our input 0, our input 1. This one I'm going to say is normally closed. And this one is normally opened. And these are tied to the select. When the select is high, it closes this one and passes this signal through. Let me switch colors here. Oh, that's a terrible pin. When the switch is high, this one is going to go, this one will go through like that. What the hell? You know, I haven't used this program in a couple years. It's really gotten better. That's cool. We're not going to use that anymore. No, we're going to use that one. No, we're not going to use that anymore. Jesus. I'm not mature enough for this power. Okay. Why do we care about analog mux? You told me that the UDO board has 6 analog inputs inside the UDO board. Here's our UDO Neo. We got 1, 2, 3, 4, 5, 6 analog pins, A0 to A5. Very similar to an Arduino. We're just going to have this. All these feed into here, and we're going to have a mux here. We got 6 inputs, so we're going to have 3 control lines. In truth, you could use this mux for 8 pins because 3, pardon me, 2 cubed is 8. We're not going to use 8. We only have 6. And then this actually goes into the ADC. And then the output of there feeds to the rest of the UDO board. You can access this with Python, get your number. Cool. But 6 is not enough. Crap. We really hoped it was. Unfortunately, we need maybe 11 inputs. I got to do a count. This is what it looks like. We got a ozone sensor. It's coming out with 2 lines. We got a working electrode and an auxiliary electrode. This is our O3 sensor. We got carbon monoxide sensor. 2 of those. We got an SO2 sensor. 2 lines there. We got NO3. Ugh, I'm ashamed. NO2, thank you. Nitrous oxide. Any of you tried nitrous oxide, like at the dentist? It's really cool. Also called laughing gas. because when you're breathing it, everything is funny or just okay. You're going to the dentist. You need to have a tooth pulled or a other terrible procedure. The dentist gives you the gas. And then he says, hey, do you mind if I stab you? And you say, do anything you want, man. I'm so high. The thing is, once you get off the gas, it takes maybe 1 minute before you're sober again. You can drive immediately. The high is it's gone very quickly. I don't encourage you to do drugs, but if you're at the dentist and she or he says, would you like to try the nitrous? Definitely do it. Definitely do it. Unfortunately, in this program, we're never going to have a high enough quantity or concentration of nitrous to actually feel any effects. We're going to be looking at, you know, parts per billion instead of just parts. Okay, so we got 8 lines here. We also got temperature sensor. We got a really cool temperature sensor, just 1 line out. Awesome. And then we're going to have the last one here is a PM 2.5 and maybe a 10 as well. This could be 1 or 2 lines. And all this, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 analog signals that we need to measure. And we can't fit them in the UDO mux. There's only 6. What do? We get, who knows? Who knows? Anyone? A bigger mux. That is correct, sir. What? Yes, a bigger one. Thank you. We're going to have, oh man, this thing is just, yeah, a monster. Woo! We're going to have 4 input lines coming from the select. And then we're going to feed all of these straight into the UDO. So here's our UDO. We're only going to use 1 analog input. It's going to go into there. We're going to have 4 digital outputs. These are all digital. How about D0 to D? Jeez. How about D0 to D3? And these are going to merge together and use that for our select. And this is how we're going to cheat 11 inputs into the UDO board. Now, actually, this mux, we call this a 16-to-1. We could have 5 additional inputs. You think of something else you want to measure as part of your project? Maybe a dog's heart rate? If you can do it with an analog to digital converter, we'll slap it right here in the same program. Anyway, of course, we're still going to have this mux in here, but we're not really going to use it. And then we have, our digital output. We can actually use that to do some calculations. Oh, a lot of arithmetic. It's going to be so cool. In some projects, maybe you need a better ADC than this one. I'll come up here. I'm losing it. Here we go, 12 bits, I told you. This is a 12-bit ADC. We call it 12-bit because we get 4,096 outputs. You can get a better ADC than that. You might say, wow, how good do they get? How fast do you want to measure is my question. You can get a 16-bit ADC. Nothing to it. 16 bits are output 0 to 6, 5, 5, 3, 5. Now, unfortunately, it's really hard to get one of these with 16 lines on the output. Doesn't exist. Well, maybe it does, but they're really expensive and we don't really care for this project. If you get an ADC that has this many bits on it, probably it's going to be a serial interface like I2C or SPI or some similar protocol. These are really common. I use them in a lot of my projects. They are so cool, especially for this project where you don't need a high data rate. Why does that matter, that you don't need a high data rate? Well, let me teach you how we're going to cheat. Yeah. Someone's excited now. He says, I love cheating. This is the best. Why try when you can cheat? So, when you take a measurement of, let's say, this O3 sensor, how are you going to actually turn this from the analog value of a working electrode and the analog value of the auxiliary electrode? And you're going to also have to take the temperature, actually. We'll take that real quick. And how are we going to take these three things and turn it into concentration of ozone parts per billion? Well, it starts with, you're going to take this AAE number, you're going to multiply it by some constant that you get from the calibration from the manufacturer, and then you're going to adjust that also with another constant that you get from a lookup table, which is temperature based. And then from this, you're going to subtract the analog value of the working electrode, and then once you have all of these together, you're going to multiply this by another constant, you know, call this C1 and C2, which also come from the calibration data, which we will provide. And then this comes out, you know, I may have forgotten a couple steps, but either way, this is going to come out to concentration ozone parts per billion. Now, unfortunately, 12 bits in this context is not a lot of bits, because if you say, let's see, I got this, my AAE number was, this is the digital number. Sorry if I didn't make that clear. If your AAE, this is the analog number, no, ignore the analog number. If your digital number, because we only care about the digitized value, is 63, and your working electrode number is 65, and your temperature is probably 25 Celsius, all of this gives you a parts per billion of 10. That's not bad. That's pretty good. However, the converter itself is not perfect. There's a lot of noise in the system just because it is a giant computer. You're passing data over some long wires, maybe it's going through the multiplexer, and you take the same measurements 1/100th of a second later, and you get some different numbers. How about AAD? This one was remarkably stable, 63, all right. And then the working electrode digitized value is 64. That's pretty close. And the temperature is 25. And then the result of this is that your parts per billion, is -15. What the hell? You say, you can't have a negative concentration. You are correct. You've been betrayed. This is because the actual value, instead of 63 or 65, was really, I'm going to just leave that there. The actual value, the true the true value is, you know, 63.11725, and this one here is 64.4444, something like that. We make these up. And unfortunately, the precision of the measurement doesn't allow us to keep any of this crap. This is the most important part, because the error here is really good. If you say the first measurement was 170 and the second one was, sorry, not 170, Jesus Christ. If you say the first measurement was 2,000 and the second measurement is 1,975, I say those are close enough. They're pretty consistent. I wouldn't want to breathe either of them. But here at the very low range, that's going to come back to bite you. And in previous years, we've had students get real stuck on this, where they say, sometimes I get a number that makes sense. Sometimes I get a number that's impossible. Can you help me? And I say, I don't work on this project. They never asked me. I wasn't working here at the time. But I am now. You guys are very fortunate. You're going to get way better data than they did last year. And you say, Mark, how do I cheat to get these extra bits? Because I really, really would love to have all that hidden data. The answer is you can oversample. I know we're almost, well, oh shit, we're over on time here. So I'll just tell you real quickly, because the air quality is not changing at a very high rate. Let's say you measure the nitrous level, and then 10 minutes later, you measure it again. I'll be very impressed if they're different. Thank you. If you measure it 100 times in a second, probably it's going to be the same every time, but you're going to have some noise in your system. So if the true value is 63.11725, and you take a measurement, this is going to be the probability, and this is going to be the digital value that we measure. Here's our actual 63.11725. This is going to be 63, and here we're going to get 64. You're going to get kind of a cool looking bell curve. Oh, sorry about that. You're going to get a bell looking curve like this. And you're going to get more 63s and fewer 64s. What you can do is you average them, sort of. You add them all up and you interpolate. You say, instead of just measuring it once, I'm going to measure it twice. Maybe first time you get 63, second time you get 64, you average them. It's somewhere in the middle. But if you take 16 averages, now you can get a precision very, with 16 averages, or 16 samples averaged, you get 4 extra bits. Is that right? 4 extra bits. And so if you oversample, let's say that your oversampling is 1, which is just taking 1 sample. What you get out would be just 63. If you oversample by a factor of 2, you could get 63 again, or 63.5. You oversample by a factor of 4, you could get 63.25. You overfactor by a sample of 8, you could get as precise as 63.125. You oversample 16 times, you can get 63.0625 or 63.125. That is enough precision for what we're trying to measure here. And so back up here where we took consecutive measurements and you say, oh, my first one was 63 or 65 here. Oh my goodness. And the next measurement, it was just this totally different number. Now we measure twice. The first time you get 63.0625. The second time you measure, you get 63. Oh, we got a lot of noise in our system. 63.0 or 63.195, something like this. The actual difference is not going to be that great. This one, we get parts per billion equals 10. I will say 11. And here we get parts per billion equals maybe 8, something like that. That's pretty good. That's really good. You might say, can I just oversample it like 1,000 times? And I say, be my guest. But it is quite wasteful on the power consumption. If you're running off a battery, I don't recommend that you do this. That's it. That's all we got for today. Tomorrow, bring your UDO boards. We're going to actually take some measurements, analog style. So cool. And you might be wondering, how do I use this analog measurement to improve my rocket lander game? I'll show you. That's it. That's all we got. That's today's lecture.